Hey guys, welcome back to our latest calculus video. Today we're talking about polar curves again, and specifically we're going to be taking some calculus with those polar curves. So let's get ready to go. Here we go. So many of you probably know that I really enjoy JoJo's Bizarre Adventure. That's one of my favorites. So here we have one of the characters. Is that what you call them? One of the characters here, this one happens to be called Star Platinum. They have a habit of showing stats for each character in this radar graph. And as you can tell, each of the stats here for Star Platinum is maxed out, except for this one over here where he gets a C grade. I think that's range, but I'm not 100% sure. It should be range. Coming from a math point of view, we can see that if we wanted to, we could find the area of each of these triangles here, and then if we either average them or added them all together or whatever you do, that would give you an overall evaluation from each character. And if you have a character with all weak stats, D's and C's, and God forbid they get an F, but if you added that area, you would get a character that isn't quite as powerful as an area as a character where all the stats are maxed out, kind of like this guy is. So that makes me think about polar area, because when you're adding together all these triangles, that's really what we're going to be doing in our polar geometry. We're just going to be adding a bunch of triangles together, although we won't be actually adding triangles together. So we're going to start off with this formula here that is from your geometry. And what is that formula? That's the area of a sector of a circle. So notice that the pi r squared part, that's just the area of a circle. Right here, area of a circle. And this right here is a proportion. So what you're looking at, for example, let's say you wanted to find the area of 1/4 of a circle. Well, 1/4 of a circle would be 90 degrees out of 360 multiplied by pi r squared. And when you simplify that, what a surprise. The area of a quarter of a circle is a quarter of the area of the circle. Okay? Not really all that big of a deal. Once we get into calculus, we've abandoned degrees in favor of radians. And instead of 360, we have 2 pi theta, 2 pi radians, so theta on top of 2 pi radians, multiplied by the same area formula. So for example, let's say we do 3/4 of a circle. Well, 3/4 of a circle, that would be 3 pi over 2 radians divided by 2 pi multiplied by pi r squared. So we get cancel. This becomes 3/4 of pi r squared, which again is 3/4 of the circle. So the area of a slice that encompasses 3/4 of the circle, well, that's 3/4 of the area. All that makes sense, and if it did, then thank your geometry teacher. All right, moving on. Let's take it to the polar curve. Over here, we've got our polar curve, and we've got the area of a slice. And the key here is to figure out, well, if I want to find the area of this slice, wouldn't this be an approximation if the radius on the left and the radius on the right were the same? In essence, if this is a sector of a circle, so the area is approximately equal to the area of a sector. Well, what is the area of that sector? Well, the area of the sector is that formula we just learned. 1/2 r squared theta. Okay. So if I want to approximate the area of a pizza slice of my polar curve, all I need to do is find the area of the corresponding sector, and that would be an approximation. That should make sense. And again, if it makes sense, thank your geometry teacher. How about here? Well, if I wanted to find the area of a whole section here, maybe one thing I can do is, instead of doing one pizza slice, maybe I do 3 pizza slices. So here we see area 1, area 2, area 3. You notice that each of those pizza slices have slightly different radii, and they have therefore slightly different areas. But the area is still governed by that same formula, 1/2 r squared theta. So over here, you have the area is 1/2 of the first radius squared plus 1/2 of the second radius squared plus 1/2 of that third radius squared. If you make all those thetas the same, then really the theta you can think of as a delta theta. And then this is dangerously looking like calculus, right? When you add it together, you get this right here. Theta equals 1/2 r squared delta theta sigma, all of that added together. And so if you wanted to find the exact area under this curve, it's not even under this curve anymore, the exact area of each of those pizza slices, you would make your delta theta get really small, and then you'd add a bunch of pizza slices together, enough pizza slices to cover that entire sweep of the curve. So basically you're saying the area is equal to a limit as delta theta approaches 0 of all of these pizza slices added together, and there's going to be a lot of them. You know, you could imagine that if you had 3 pizza slices, well, that area approximation is going to be nowhere as good as if you had, for example, 100 or 150 or 200 or 1,000. So eventually, the more pizza slices you have, the closer delta theta comes to 0. And isn't that the idea of a Riemann sum? Yes, it is. I'll answer the question for you. So the area is equal to, we know from our calculus that this turns into an integral from theta 1 to theta 2. That's what happens here. This 1/2 stays a 1/2. This r squared stays an r squared, and delta theta becomes d theta. Now remember, r is equal to a function of theta. So you're squaring functions. You're not squaring a constant unless you're talking about a function where the radius is constant. So you're squaring a function. So if we're squaring a function, I should probably say here is that formula. You want to put this in a box. You want to write this in your notes. This is the one. There's a slight alteration here to make sure that this formula works compatibly with the other ones that we've used, and that is just to call those upper and lower angles A and B. Okay, one important thing is this formula only works if each radius drawn from the curve extends all the way to the pole. So for example, if I have something like this, and I want to find the area of this slice right here, this won't work because the radii doesn't go all the way to the pole. So that means my area formula won't work. Okay, so that's a pretty easy thing to do. All you need to do is keep drawing a bunch of radii, and if any one of those radii doesn't go all the way to the pole, or if the region doesn't go all the way to the pole, then you can't use this area formula. You got to do something else. From experience, I know that Some people are not going to be integrating a function. They're going to be about finding the radius at one or other part of the region and then just integrating a constant radius. And that's not going to work. Your radius in polar curves is a function, so make sure you're integrating a function. By that same token, since we're integrating the square of the function, we're mostly going to be using a calculator unless our integrand simplifies really nicely into something that we can integrate. So have your calculator ready, and we're going to start now. Now there's only one formula in this entire second day of 11.3, and that is the area formula. Think radially, and what I mean is think in terms of radii. You've got to think in pizza slices, which shouldn't be hard because I know most of us love pizza. So think in pizza slices. Don't think in terms of in rectangles. This is not the best way to think of these. No. Okay. Doesn't work. Think in terms of pizza slices, okay? So now I think we're ready to go with our check your understanding. Let's find the area inside the limacon r equals 4 plus cosine theta. Well, maybe the first thing we should do is draw that limacon. So let's get a coordinate axis over here. All right, limacon 4 plus, that means the major axis is going to be on the right side of the graph. The major axis is going to be 4 plus 1, or 5. So this is at 5. Our minor axis is going to be at 3. Our side axes are going to be at 4. Is this going to be dimpled? Is this going to be convex? What's it going to look like? Honestly, don't care. I think it's just basically going to look like a deformed circle, personally. So here we go. First thing to notice is that from 0 to pi radians, that is symmetric to pi to 0. So we're going to make use of that symmetry. And we're going to make use of that symmetry. Always got to make use of that. All we need to do is use our formula. Area equals 1/2 r squared d theta from 0 to 2 pi. Okay, I said we're going to use symmetry, and I mean it. Area is just equal to 2 times the area from 0 to pi of 1/2 r squared d theta. Okay, so that takes care of the 1/2. So the area is just equal from 0 to pi. My radius is 4 plus cosine theta squared d theta. Grab your calculator. Remember, there's no need for you to put this into polar mode. This will work just fine if you are in function mode in your calculator. So got that radius in y1. Going to go to the home screen, and we're going to integrate. Math 9, integrate from 0 to pi. And what is that? My r was in y1, so y1 squared, and I'm using x for theta, and that should do it for me. 51.836, 51.83, 62.7, 51. 67.2. Okay? Notice pi does not even make an appearance in the integrand. it's not part of the formula. So those of you who get used to integrating this all the time, I don't know what to tell you here. Things get a little different if we try to do a 4-petaled rose here. Let's graph that real quick. Okay, so it needs to be symmetric around the y-axis. There needs to be 4 petals. The first petal, possibly more petals, need to be in the first quadrant. So what I think we're going to see is basically a cloverleaf. Part of my idea of this cloverleaf is I've graphed more than a couple of these polar functions in my lifetime. And if you want to be really good at this, you're going to need more than one semester of graphing polar functions, I'll tell you that. So having a little bit of experience here helps out a lot. So basically, every time you see a polar graph, you should be graphing it on your calculator just to see what it looks like, just to see how the path of the particle moves. So here's my cloverleaf, and for a 4-petaled rose, my plan, and maybe I should type this out, the plan is to find the area of a petal and multiply by 4. That seems pretty reasonable, and the main reason why you want to do this is that at some point you're going to have negative radii, and even though the radius is squared, things could happen and you don't want to deal with that. You just want to find the area of one petal. So a petal starts and stops when r is equal to 0. For any rose curve, the petal starts and stops when r equals 0. So for us, that means we're looking at when is 3 sine 2 theta. You'll use an x here. When is that equal to 0? Okay. And I put a 3, and it should have been a 2. So when does that happen? Let's do a little bit of solving. Certainly, if you want to use your calculator to solve, I wouldn't mind at all. So divide by 3, sine 2 theta equals 0. So when is sine 2 theta, or what are the first 2 times in the unit circle that theta is equal to 0? Well, that happens when the angle, I shouldn't say theta, the angle that sine is equal to 0 first happens at 0 radians, and then it happens again at pi radians. So the angle 2 theta has to equal 0, or the angle 2 theta has to equal pi, giving us theta goes from 0 to pi halves. One petal, that's going to be equal to integral from 0 to pi over 2 of 1/2 r squared d theta. So 4 petals then, that's going to be 4 times that same integral. Or if you simplify that, that is 2 times the integral from 0 to pi over 2 of 3 sine 2 theta squared d theta. Again, grab your calculator. We have our radius in y1, which is what you should be doing. And then on our home screen, we're going to put 2 times this integrand. Two times the integral from 0 to pi over 2, right? and push enter, and this is the area of all 4 petals. 14, 13, 71, 6.
14, 13, 71, 6.
Not that bad, is it? No, I don't think it's that bad at all. You really need to think in terms of pizza slices. So this is the time when calculus means pizza. Got to think of those pizza slices, and good luck with your area of polar curves. Trust me, it's not that bad. No matter what anyone tells you, it's not that bad. All right, I'll see you next time.